So your seating chart is up. You can go ahead and do your seating chart. I want to see which one. Yeah. Okay. All right. Okay, so it should be pretty quick. I'm not watching the time now. Okay, so we are new. So how do you make a mouse smile? Say cheese. Say cheese. Right? Okay. So what I want to do is I want to finish. Oh, no. Did I not open that one? I think I didn't open it. I think I have one more file to open. Oh, and I didn't finish in doing eye clicker. Oh, my goodness. Not doing so red hot here. Okay, and then, okay, so you have your eye clicker out. You have your best friend. Everybody have their best friend? You're gonna need your best friend. We're finishing chapter 8. Finish chapter 8. Okay, so we got like just a few quick questions, and then we're gonna do some eye clicker in just a minute. So we're gonna finish chapter 8 real quick, and then we'll do some eye clicker questions on chapter 8. So we were at the very end, right? We had finished 8.6. We are on 8.7, right? Yeah. Okay. So when we finish 8.7, let me minimize this stuff. So this, the last thing is really talking about how molecules are going to cross the membrane, right? So some things cross all on their own, and some things have to be transported across. And there are multiple ways that they can be transported. Everybody remember mask up over noses and mouths, please. So when we talk about molecules and their movement, right? They're always going to move according to diffusion from an area of high concentration to an area of low concentration. And that happens spontaneously, right? So just like if you're making a drink, right? And you have like Crystal Light or whatever the liquid one is, you squeeze it into your water. And even if you don't shake it up, if you leave it there for long enough, what's eventually going to happen, right? You stream in this colored, sweet, whatever flavor floats your boat, you know, strawberry lemonade or, you know, mango iced tea, whatever it is. And you stream it in, it's very high concentrated when you stream it into your water bottle, but what happens eventually? Just by diffusion, all those flavor molecules are going to get dispersed inside of the water. Why are they doing that? It happens spontaneously. It's just diffusion. It's just particle movement diffusion. The warmer it is, the faster it'll happen, right? So the same thing is true inside of our bodies. We have molecules that move and things like that. And you have to think that some molecules, right, are going to be able to get in the cell all by themselves. For example, oxygen, right? Oxygen, tell me about the properties of a molecule of O2. O2. If I were to draw O2, what does O2 look like? How many valence electrons in oxygen? 6. So how many bonds is it going to make? How many bonds is it going to make to form an octet? 8, right? So now we have 2 lone pairs, and usually we draw them we draw them this way. I'll show you how we draw them. We usually draw them as kind of like at an angle there, like that, all right? So do we have a polar or a non-polar molecule? First thing you're looking at is, do you have electronegativity difference? Do you have an electronegativity difference between oxygen and oxygen? No. So do you have a polar or a non-polar substance? It's non-polar. Do you have to know how to identify polar and non-polar substances? Yes, and you're terrifying me just a little bit. So we have a non-polar substance. Really small non-polar substances are going to go across cell membranes through passive diffusion. So small non-polar go through passive diffusion. Small non-polar. They don't need any help. It's passive, right? So which way would water molecules, which way would oxygen molecules move? Would they move left to right or right to left? The blue arrow or the red arrow? Blue. They would move by the blue arrow. Okay. So we're gonna erase this one. So that's the direction of movement of our small non-polar molecules. They go from an area of high concentration to an area of low concentration, right? So when we're looking at things, we have to decide whether they're going to be able to go through passive diffusion or if we're going to have to help them. So there are two different ways that you can help molecules get across a cell membrane. You can have what's called facilitated transport. Facilitated transport means there's like a tunnel, right? Does anybody have to maintain a tunnel? No, you just drive through it whenever you get there, right? That's facilitated diffusion. You have a tunnel that's helping you get from place A to place B, but there's nothing carrying you, right? Active transport is more like a ferry, right? There's a boat that you have to get on, and the boat has to run, and it uses energy to get from one place to another, right? That's active transport. You're working on it, right? So let's look at each one. Oxygen, what happens with oxygen? What did we just say? It's a very what? This is a small non-polar molecule. So how will it move? Passive, it doesn't need any help. So things that undergo passive diffusion are things that are small and non-polar and also water, right? Water is going to move passively. It also has a facilitated transporter, but it can passively transport as well. Okay, glucose, no energy required. Tell me about glucose. What kind of a molecule is glucose? Polar or non-polar? This is glucose. And these are hydroxyls. Polar or non-polar? Throw it out there, anybody? Got a 50-50 chance. Polar, absolutely polar, because it has all those hydroxyl groups, right? So they can participate in what kind of bonding? Hydrogen bonding with water, all right. So it is polar, glucose is polar. So is something that's polar going to get across the membrane? No, we just said that you have to be kind of a small non-polar molecule other than water. Otherwise you're not getting across without some help. So because it's polar, it needs help. But we're saying no energy is required. So is that facilitated or active? So facilitated. Facilitated transport. Sodium ion, energy required. Do you see how this is this polar or non-polar? It's even more than polar. It's charged. This thing is not getting through the membrane unless it has help. So it's either going to be facilitated or active. But now it's saying energy is required. So is it facilitated transport or active transport? Active. Okay, and the last one is also a positive charge, but it's saying no energy is required. So what kind of transport is that? Facilitated. Oh. Okay, thank you for trying on chat. I'm going to keep my chat up. All right, cholesterol, no energy required. So remember, cholesterol had one end that was kind of polar and the other end that was lots of carbons and hydrogens, so it was very non-polar. Yeah, so because it has that one polar end, it's not going to go all by itself. So it's going to need help. So cholesterol is going to need help because it's partially polar. Right? So is it going to be facilitated or active? How do you know facilitated? No energy. So this is facilitated. Okay, nitrogen. Nitrogen doesn't exist all by itself. It's always going to exist in the diatomic state, so N2. So polar or non-polar? It's non-polar. It's two nitrogen atoms hooked together. It's non-polar. So if this is non-polar and it's small, it's just two atoms, it's tiny, what kind of transport are we going to have? Passive diffusion. Okay, Cl minus, no energy required. Because of that minus sign, it's not going to be passive, but no energy is required, so it is facilitated. H plus, energy required. This is going to be active. It's charged and we're using energy, so active transport. And that is the end of chapter 8. Question. Y'all ready to do some eye clicker? All right, let's do some chapter 8 eye clicker. All right, here we go. All right, view full screen. All right. So what is the molar concentration of a lidocaine solution prepared by diluting 5 mils of a 1 molar lidocaine stock solution to the mark in a 25 milliliter volumetric flask? That means that this 25 milliliter volumetric flask is your final concentration or your working solution. Okay. So there's a formula, and I'm going to give you 3 minutes to do this one. I'm going to give you 3 minutes to do this one. Okay. 3 minutes. Try to make it. There we go. Three minutes. Coming up on 20 seconds. Make sure you click in and give some answer. Attempt an answer. Okay. So turn and talk to the people around you. Come up with a second answer. "45 seconds. Don't forget to click in again. Everybody click in again. Uh-oh, not good. All right, so what formula did you use? CI VI is equal to CF VF, right? Okay, so we're diluting 5 milliliters of a 1 molar lidocaine stock solution. So the stock is always our what? Our initial, right? So we're going to have a concentration of 1 molar, a volume of 5 milliliters, right? Now, we're filling it to the mark in a 25 milliliter volumetric flask. So that's our final volume, 25 milliliters, right? And our question is, what is the final concentration? So divide by 25, what do you get? So you should have gotten 0.2. Yeah? Okay, so let's see what we got. Oh, yay. So we definitely went up. We definitely went up. So what do you think? What do you think the issue was here? Deciding what formula to use? Yeah. So all the time when you're looking at, I'm taking a stock and I'm making a dilution. I'm taking a 1x and I'm going from a 25x to a 1x, or I'm diluting from a 1 molar to something, right? Whenever you read the question and you think, oh, I'm diluting something, pull up that CI/VI is equal to CF/VF. Okay, so get really comfortable with that one. Okay, and that's what I just did. I keep forgetting that I have the answers. Can't help myself. Okay, so let's try another one. This is really similar to what we were just talking about. So select the correct statement regarding solutes crossing a cell membrane. Okay, so read each statement carefully. Okay, coming up on a minute, so make sure you click in. Forgot to give you the 10-second warning. So at 1 minute, 10 seconds, I'll close it. Okay, turn and talk to the people around you. Y'all use that chat function on Zoom so y'all can talk like the rest of the class. I'll end it at 45 seconds. Okay, getting close, 5 seconds. Make sure you click in again. Don't forget to click in again. All right, so what did we say? Okay, good. So it is B. Oh, 100%. Awesome. I love seeing that. All right, so let's look at each one because I just kind of want to address each one. Magnesium ions, Mg2+, are more permeable than small neutral amino acid molecules. Why is this one not true? Smaller neutral would be more permeable. So you could change this just by saying less, right? It's the opposite, okay? So he said B is correct, that water molecules are more permeable than sodium ions, right? Ions are harder to get across because they're charged, right? They don't slip through the membrane very easily. C, sodium ions, Na+, are more permeable than oxygen molecules. No, right? Oxygen is what? Small nonpolar, small nonpolar. So sodium ions are, again, less permeable than our small nonpolar oxygen. Proteins are more permeable than glucose. Think about proteins. When we say proteins, is this something big or small? It's really big. It's really big. It's usually charged, usually carrying some kind of a charge, right? So they're less permeable, right? So each one of the incorrect ones, all you had to do was swap them and say less, all right? Okay, one more. One more. Okay, select the solution that could cause red blood cells to hemolyze or burst. You have to remember what physiological conditions are. So if you haven't learned that, let's go learn it. I'll give you a minute and a half or 2 minutes on this one, actually. I'll give you 2 minutes because you got to kind of think about this one. 2 minutes. Okay, about 10 seconds left, so make sure you take a guess. Okay, turn and talk to the people around you. 45 seconds. Okay, 10 seconds. Make sure you click in again. Okay. All right, so what did you do to make this decision? Before I expose the answer, what 2 pieces of information did you need to know? Physiological conditions. So what are physiological conditions? We have something for salt. What is it for salt? What's the percent? 0.9% NaCl. And how about glucose? It's 5% glucose. Okay, so if the solution that the red blood cell is in is at physiological conditions, what happens? Nothing. Well, not nothing. We say nothing, but the same amount that goes in goes out. So the net effect is nothing. So be careful on that. The net effect is nothing. So it can't be D, it can't be C, right? Okay, I'm going to show you a test taking tip. One of these is not like the other 2. Which one is not like the other 2? C, why? So 1.5 NaCl is higher than physiological, right? 10% glucose is higher than physiological. 0.45 NaCl is what? Lower than physiological. Even if you didn't know what to do, that should be a red flag. So let's talk about this lower than physiological condition, right? So why would this cause the cells to burst? If I have my beaker, I have my red blood cell, and my red blood cell is 0.9%. I put it in a solution that is 0.45%. What is water going to do? Water moves to what? Higher concentration, C-O-N-C-E-N-T, concentration solute. So where's a higher concentration solute? It's in the cell. So water is going to go in and make the cell burst. Yeah? So more than one way to answer, one way to get to the answer. Okay, so that was question number 6. And what am I looking for? What was my correct answer? It was C. Okay, so C. Oh, it was not good. That was really, so we knew it wasn't 10% glucose. If you know it's not 10% glucose, you should be able to eliminate A. And you should know B and D were physiological, right? I'm telling you that there will be something like this on the exam. There will be something like this on the exam. Okay? Good? All right. Sometimes it's good to find out that you don't know something in an iClicker question than on the exam. Okay. So let's go and work on some chapter 9 stuff. Full screen. Okay. So this is our last chapter, y'all. This is the end. How you feeling about that? Kind of good, kind of not. Yeah, I empathize with that feeling. I completely empathize with that feeling. It's kind of crazy how quickly the semester is going, right? So acids and bases and buffers in the body are so insanely important. It's going to be really important when you talk about drug interactions, right? How drugs interact with the body. Buffers are really important in maintaining conditions inside the body, right? There are lots of parts of the body that if you change the pH, nothing works. And that's a really bad thing. So we have buffers in all kinds of different parts of our body, especially, for example, the bloodstream. The bloodstream is a very buffered area of the body so that we keep the pH constant. That's the whole point of a buffer, is to keep pH constant. So when we think about acids and bases, because acids and bases make buffers, so you have to understand acids and bases. then we can talk about buffers. So let's kind of talk about those two things: acids, bases. How can we distinguish an acid from a base? What is by definition a characteristic of an acid? We talked about acids in the last chapter a little bit when we talked about things disassociating. Do you remember that? What disassociated for an acid? If I have, for example, hydrochloric acid, this is an acid that's inside your stomach, right? Your stomach has a really, really low pH, so it has hydrochloric acid in it. HCl, if I put this in water, what's my dissociation reaction? What's one of my products? Y'all, there's two atoms there. Hydrogen's one of them, and chlorine's the other. So now that I've separated them, they're going to be charged, right? So what's the charge on chlorine? -1. Therefore, in order for my original compound to be neutral, what must be my charge on hydrogen? Positive, right? Okay, so this is a great example of an acid. What disassociated? What's going to be true for every single, almost every single acid? What is going to disassociate? A hydrogen ion. So an acid will make hydrogen ions, and that's what we use the H+, hydrogen ions, in water. Another way to say that is acids will donate H+, or hydrogen ions. Well, if that's what acids do, bases are basically the opposite. So what could you say about bases? Well, accept H+ ions, okay? What happens when we put it in water? We can't make H+, but when you think about water, water is H2O or HOH, right? So if you can't donate hydrogen ions, what's the other part of water? Hydroxide, OH. So we'll make OH- in water. So let's talk about some characteristics of acids and bases. Where might you find acids in your body? Are you listening? In your stomach. So stomach acid. What are some things that are acidic that we like to ingest? Things that are sour are acidic. Sour is our ability to taste acid. Lemons, citrus, right? And who likes some good salt and vinegar potato chips? Yeah, that's me. I like that. So vinegar is another, V-I-N-E-G-A, vinegar, right? Okay, so let's talk about bases. So bases, bases have a characteristic that they're very, very slippery, right? So when you wash your hair, when you wash your body, the soap is basic. And that basic characteristic gives it that slippery feeling. So you could say soaps. Toothpaste is another one. Very basic. So when we look and we compare these two on the pH scale, pH is a measure of how many hydroxide and and hydrogen ions you have. So pH, so if you have a high pH or a low pH, right? If you're right in the middle, you're neutral. So if you have a really low pH, are you an acid or are you a base? Tell me. So, and I'm going to give you a trick. Hold on. Go to your best friend. There's a whole page that starts acids and bases. So I want you to have your best friend out so you know exactly what you're going to have on the exam. You know, there might be some interesting tidbits on there. So if you have an acid, look at your best friend. What's the pH of an acid? Above 7 or below 7? Below. Acid has a low pH, so it's below 7. That's that less than sign. So how about a base? High pH, and it's above 7. So when we think about acids and bases, if I combine a little bit of an acid with a little bit of a base, what do I make? An acid donates H+, a base donates OH-. If I have a little bit of an acid and a little bit of a base, what do I make? I have how many hydrogens? How many oxygens? What do I make? Water. You also make a salt, but we'll get to that. So look at the first question, 9.2, neutralized by a base. So this is basically a neutralization reaction where you have an acid being added to a base and you make water. So what is neutralized by a base? Neutralize means get to pH 7, which means you don't have an acid, you don't have a base, all you have is pure water. So an acid is neutralized by a base, right? Acid plus base equals to water. So here's my acid, here's my base. Acid plus a base makes water. So this is neutral. Okay. Produces OH- in water. That's a base. Has a slippery feel. That's a base. Donates a proton. How do you know that? What is a proton? A proton, right, is one proton. It's part of the nucleus, right? So it's the same thing as a hydrogen ion. If you have a hydrogen atom and it is charged, that means it has lost its one electron. And because if you look on the periodic table, what's the mass of hydrogen? 1.01. So do you have any neutrons in there? No, because if you had a neutron and a proton, your atomic mass would be basically 2. But your atomic mass is 1. And to be hydrogen, you have to have one proton. So one proton has to be there. So if it's charged, that means it has lost its electron. And it is now just what? A proton. So you will see proton and hydrogen ion used interchangeably in the text. And you have to understand that that's okay to do. So now, in an aqueous solution, what does that mean in an aqueous solution? Aqueous solution means in water. H+ and H3O+ represent similar things. So how is that true? Well, if I have a hydrogen ion It's what charge? +1, right? And I also have a water molecule. Is my water molecule charged? No, it's not, but tell me about water. Because this isn't a good enough picture of water, right? I need to put my lone pairs. And what else do I need to put? Why is water so freaking amazing? I'm going to ask you this on the last day. You all need to chant in unison. It's polar. It's polar. Water is polar. That's why it's so freaking awesome. So tell me about the polarity of water. Oxygen's that electron hog, right? He wants all those electrons to himself, so he takes the electrons away from hydrogens. So the hydrogens are partially positive. Oxygen is partially negative. So what can occur between the hydrogen ion and the water? I have a positive and a partially negative. What kind of an interaction is that? Close, almost. I have an ion and a what? And a dipole. So I have an ion dipole interaction. That ion dipole interaction is really, really strong. And what actually ends up happening is that you create a covalent bond with the other hydrogen. Isn't that crazy? So you have an extra hydrogen. That extra hydrogen gives this H3O molecule a positive charge. So you do have another lone pair still on there. And you can put a plus there. It's a full positive. It's not just a dipole, it's a full positive. So hydrogen ions, these guys don't exist. We pretend that they do, but they don't really exist all by themselves, because if they're close to water, they're bonding with water. They love water, right? So really we have H3O+. So anytime that you're in solution and you make hydrogen ions, you could also say H3O+. It's the same thing. Okay. All right, so let's look at some reactions where we put acids and bases in water and see what happens to them. Okay. So in each of the equations, we have to identify the reactant that is an acid and the reactant that is a base. So we know that our acids donate hydrogen ions, and we know that our bases accept hydrogen ions. So they very nicely wrote this equation for us. So we have something that is H3PO4. We're going to react it with water. We're going to make H2PO4 minus, right? We lost a hydrogen here, so it becomes negative. And then we have H3O plus. So tell me who donated. Let's talk about the donor first. Who donated a hydrogen ion? H3PO4 donated a hydrogen ion. So this is an acid. It is the donor. Because when we go and we look, we see, oh, it's lost a hydrogen. That's how we know. We started with H3PO4, we ended with H2PO4. So now what is a base? Base is something that does what? Accepts hydrogen ions. So what molecule has accepted a hydrogen ion? Right here, we have a base because it started out H2, and then what was it? it became H3O+, so it gained a hydrogen. That is my acceptor molecule. Okay. How about in B? Tell me about my acid first, my one that's going to donate. H2O. There's only one molecule on the reactant side that has a hydrogen, right? So this has got to be the acid. And if I look, my H2O has turned into OH minus. So it has lost my hydrogen. Well, where did that hydrogen go? Is it just floating around? No, somebody picked it up. A base picked it up. What base picked it up? PO4 3- is my base. This is the acceptor. And I can check that. I can look and I can say, okay, here was my base. I went from PO4 3- to HPO4 2-. Okay, pretty good. All right. So now, there are different types of acids. Some acids are like super happy to give up their hydrogen. They 100% disassociate in solution. What do we call those? Something that disassociates 100% in solution. Disassociation. Like HCl, 100% disassociating. I do it as a single arrow. I get H plus Cl minus. This is in water. What do we call that? Non-electrolyte, weak electrolyte, or strong electrolyte? This is a strong electrolyte. So some things disassociate, some acids disassociate completely. We call them strong electrolytes, but if they 100% disassociate and they are acids, we also call them strong acids. You could have weak acids. For example, over here, H3PO4, is it disassociating 100% in solution? How do you know that? You're shaking your heads no. That is the correct answer. How do you know that? You're right. How do you know that? What are you looking at? The arrow. Look at the difference in the two arrows. 100% disassociation is 100% one way, right? A partial disassociation has that double-sided arrow. So I know that H3PO4 is an example of a weak acid. A weak acid does not disassociate 100%, right? It's partial disassociation. So we call this a, what else? What's another word for a weak acid? We can call a strong acid a strong electrolyte. We can call a weak acid a weak electrolyte, right? Okay. Now, it's going to be important that you're able to recognize strong and weak acids and bases. Everything we talked about for acids is true, and the same is true for bases. So do y'all mind if I erase some things so I got some more room? Y'all okay? All right. I'm going to erase some of this stuff just so that I have a little bit of room to work. Okay. So how do we know just by looking at a substance if it's a strong acid or a strong base? Well, when we talk about acids, there are two kinds of acids. There are binary acids. What does bi mean? Two. Binary acids mean we have two atoms. So for example, HI. How many different atoms are in HI? 2, hydrogen and iodine. How many are in HBr? 2, hydrogen and bromine. How many are in HCl? 2, hydrogen and chlorine. So there are 3 binary acids that are strong acids. The way that I remember this is I say to myself, I bring clay. I don't know why, but it works. So I remember my binary acids by remembering the phrase, I bring clay. Now, in case you forget that, go look on your best friend and you have this table of 6 common strong acids. Do you see the 3 binary acids? HI, HBr, HCl, I for iodine, Br for bromine, so bring, and then clay, Cl for clay. I bring clay, right? That's how you remember these are strong, but they're really on your best friend. But it's just nice to know that, so you don't have to go searching a bunch. Now, there are other acids that have hydrogen, and then what is this is an example of? ClO4. Where might I find ClO4 on my best friend? On my polyatomic ion table, right? So anything that is hydrogen attached to a polyatomic ion is called a tertiary acid. So it has at least 3 different things in it, right? So here's the rule for those. If you have 2 more oxygens than hydrogens, you are strong. So let's see if that fits our examples here. I need 2 more oxygens than hydrogens. Perchloric acid, how many hydrogens do I have? I have 1 hydrogen, how many oxygens? 4 oxygens. Do I have 2 more oxygens than hydrogens? Yes, I actually have 3 more, right? Okay, sulfuric acid, how many hydrogens? I have 2 hydrogens, and how many oxygens? 2 oxygen, 4, if I could read. So if I have 4 oxygens, that is 2 more than the 2 hydrogens. So that checks out, right? Okay, my last one. Nitric acid. I have 1 hydrogen and how many oxygens? Do I have 2 more oxygens than hydrogens? Yes, so it's strong. So you can either go to the table and use the table, or you can remember these 2 statements for strong acids. So these are strong. These are strong. Okay. All right. Now we got to talk about bases, right? Well, we're able to identify strong acids. Now we need to talk about identifying strong bases. If you want to identify something that is a strong base, it is going to be something from group 1 or strontium, barium, or calcium in association with OH, right? So it's a group 1 element. So what's an example of a group 1 element? Pick the very first group 1 element in column 1. Lithium. So like lithium hydroxide would be a strong base. Sodium hydroxide is a strong base. You see the trend? See what we're doing? Potassium hydroxide, rubidium hydroxide, cesium hydroxide, francium hydroxide. Those would all be strong. When you get to group 2, would beryllium, would BeOH, beryllium hydroxide, be strong? Is it a group 1 or strontium, barium, or calcium hydroxide? No. So this would be what? That would be weak. Okay, how about MgOH, magnesium hydroxide? That would be weak. How about calcium hydroxide? Yes, strong, right? Because it's here in the list. Okay, make sense? So it's just one thing that you really have to remember with strong bases. Group 1, strontium, barium, and calcium. Okay, so now let's look. Which of the following are strong acids? HNO2. How many hydrogens? 1 hydrogen. How many oxygens? 2 oxygens. Do I have 2 more oxygens than hydrogens? No, I do not. So this would be weak acid. Okay, how about B? HNO3. Now you could just go look at your table and say yes, but I don't always want to do that. I want to say I have 1 hydrogen and I have 3 oxygens. So how many more oxygens do I have than hydrogen? 2. So it is strong acid. Okay, so we're going to circle this one. This one is a strong acid. H3PO4. I have how many hydrogens? 3 hydrogens. How many oxygens? How many more oxygens do I have than hydrogen? Only 1. So strong or weak? Isn't that kind of a nice trick? Yeah. I love little tricks. Okay, which of the following are strong bases? All of our strong bases are going to be in group 1, and then we have a few in group 2. What are our few in group 2? Strontium, barium, calcium. Okay, so MgOH2. Mg is in what group? Group 2, but is it strong? No. So this is a weak base. NaOH is in what group? Group 1. So is it strong or weak? Strong, strong base. So this one is a strong base. FeOH3 is weak. Pretty, not so bad, right? If you know the rules, it's not so bad. Okay. Which of the following compounds completely ionizes in water? What does that mean? Completely ionizes in water. It's going to be a strong, either acid or a strong base. Excuse me. So LiOH. What group is Li in? Because I see a hydroxide there, so I'm going to go to group 1. What group is Li in? Lithium. It's in group 1. So strong or weak? That's a strong base. So this will completely ionize in water. H2O. What happens with water in water? So here's the deal with water, right? Some of the water is going to disassociate. So we actually have a double-sided arrow where we make hydrogen ions and hydroxide ions. It does that. It spontaneously ionizes. It's a characteristic of water. But is this a strong acid or base, or it's making both, right? It's donating both hydrogen ions and hydroxide ions. So it's both a weak acid and it is a weak base. So it actually does both. Okay, C, benzoic acid, C6H5COOH. Oh my goodness, we haven't seen something like that before, right? That's really weird. Here's a trick, here's a tip. Come up, you know your little things up here, strong acids. Here's my thing. Anything So this is really, it's really a base. But anything with carbon is weak. Anything with carbon is weak. So if you see carbon, automatically think weak. Okay, so if I come down here, do I see carbon? Absolutely. So what is benzoic acid, strong or weak? It's weak. So if it's weak, does it completely ionize? No, it doesn't. So this is actually a weak base. Weak acid, sorry, not base. Weak acid. You can go either way. Okay. So now, you have to be able to name acids and bases. I know it's probably not your favorite thing, but it's really not bad. Because you're given the table of polyatomic ions, you've really got everything you need there. The only other thing you need is on the acids and bases page. Do you see this little table that I put here? I put you that table on your best friend. It's there. So if you get confused, you just go and read the instructions and it tells you how to name it. Okay, so let's talk about this. You know how we said there are two different types of acids, right? What are the two types? That's true. That's true. What are the two types of acids in terms of number of atoms inside of the acid? Binary and tertiary, right? Binary meaning we have two atoms. The way that we're going to name something that is binary is that we're going to say hydro, because one of the two atoms is going to be what? If it's an acid, hydrogen. So that's where the hydro comes from. HI, HBr, HCl, right? All of those are hydrogens. So we're saying that one of those two atoms is hydrogen. And then we're going to say it's hydro, and then it's the second element name with an IDE. So when you look and you're naming something on like the periodic table, if we're going to name something like NaCl, how do we name NaCl? Sodium chlor what? Sodium chloride. Okay, so if you end something in IDE, whatever ends in IDE, because it's an acid, we now end it in IC. So it would be hydro, if we're going to put it with chlorine, right? Hydro, and then you put the beginning of the element name and you end it in IC. So hydro, for the example, hydrochloric, there's the IC, and then you put the word acid, right? So the only thing that's going to change for binary acid is this little bitty part that's underlined, right? Hydrobromic acid, hydroiodic acid, hydro whatever element, put your IC and call it an acid. The binary acid naming is really easy, okay? And that's what it tells you. If you have an anion that ends in IDE, you're going to put hydro, whatever element, ic acid, right? So it's the same instructions. Now, if you have something that comes from the polyatomic ion table, what do you notice? Go to your polyatomic ion table. What do you notice about the ending of all of these names of ions? What do you see over and over again? Either ATE or ITE. So when you go to the polyatomic ion table and you find a polyatomic ion, you take that ion name and you take off the ending, and you're going to add a different ending depending on whether you started with ATE or you started with ITE. So how do you remember which one's which? You either go here or you remember one of two phrases. My two phrases are, right? Ick, I ate a humongous bite. Okay, why does that help you? Because if you ended in ATE, you're going to change to IC. If you end in ITE, you're now going to end in OUS. Ick, I ate a humongous bite, right? The other one that you could do, I've also heard, which is kind of fun, is I went to chemistry class and I got aitic-itis. So I got 8, ick, I-T-O-U-S. I got aitic-itis. So A-T-E goes to I-C, I-T-E, sorry, goes to O-U-S, right? It's the same thing. Just another way to remember it. But the rules are really here. I'm going to give them to you, right? Okay, so let's write the name and formula for the acids. So I'm going to erase some of this stuff because I'm going to need room. My goodness. Okay. All right. So if I am going to create an acid with iodide, give me the formula first. How many elements are here? Only one. So to make an acid, I just add a hydrogen and my element. My iodine was a -1. My hydrogen's a +1. I'm overall what? Neutral, right? So now I have a binary acid. How do I name this binary acid? I always start with the hydrogen. So I say hydro. Then I'm going to go find, what does I stand for? Iodine. So I'm going to say hydroiodo. Hydro, and then what do I end it in? IC, an acid. Hydroiodic acid. They're kind of fun to say. Kind of like naming acids. They sound really cool. They do. All right, perchlorate. Am I going to find that on the periodic table? Oh no, so I got to go to my polyatomic ion table, right? In order to find it. So perchlorate, I'm always going to put it with hydrogen. How many hydrogens am I going to put my perchlorate ion with? It all depends on its charge. I want to make a neutral compound. So how many hydrogens do I need to make a neutral compound if hydrogen has a charge of +1? 1. So I'm going to put HClO4. So now, what are my rules? If I end in ATE, what am I now going to end in? IC, ick. So I'm going to say perchlor. Instead of ATE, I'm going to put IC and I'm going to put the word acid. So this is perchloric acid. Once you know the rules, it's not so bad. And very nicely, I gave you the rules, all right? Okay, acetate. How many hydrogens do I need to put with acetate to make it neutral? Only 1. Now, acetate, we normally write the hydrogen on the other side of the molecule, but I really don't care. And I don't think the program cares either. If it does, y'all tell me, but I don't believe the program cares. If you write it this way, we only write it the top way because this hydrogen actually bonds to that oxygen. But it doesn't really matter, okay? So how would I name it? So take everything that's not the ATE, so ACETE, ACET, excuse me. And then what do I put on the end? ATE becomes IC, IC. So acetic, and then what do I have to say? Acid, acetic acid, right? Not too bad. Practice. I'm telling y'all to go do the extra practice that's at the end of the chapter for these. Because if you only do a few, you're going to get really stumbly in the exam. But if you go and do a bunch of them, you're going to do really well. So go do the extra practice at the end of the chapter, okay? And the odd numbered ones, the answers are there. If you do some of the even ones and you want to know if you got it right or wrong, you can always email me. Dr. B, I did number whatever. This is what I got. Is it right? You can't email me for the answer, but you can email me your answer and I'll help you, okay? All right. Now, you remember how I was saying that if you took an acid and you added it to a base, what would you make? Water, because an acid disassociates a hydrogen ion, a base disassociates a hydroxide ion. So hydrogen ion, hydroxide ion come together, form water. Okay, that's true. But if I take, let's do a different one. HCl, that's an acid, plus NaOH. Okay, what happens when I put both of these two things into water? I'm going to get an H plus what? Cl minus plus what? Na plus OH. Oh, I got to scooch that over, huh? Plus OH minus. So this H plus right here will combine with this OH minus right here, and we'll make what? Water. Look at what's left. Cl minus and Na plus. What is that? Salt. Oh. If you have a strong acid and a strong base, that's what HCl and NaOH are. These are both strong acid, strong base. They are going to react together always to form strong acid plus a strong base. Always forms a salt and water. If you have things that are weak, they kind of do some different things. But typically, a strong acid and a strong base are always going to form a salt and water. Now, the only exception to this rule is if one of those acids or bases contains carbon. If one of those acids or bases contains carbon, you also make carbon dioxide. So can also form CO2 if you have carbon there to start with. And so we're actually going to do an example today where we have carbon. So this is what, like, if you've taken any chemistry lab, like in high school and that kind of thing, if you had leftover acid and your teacher was like, no, don't dump that down the drain, right? You can't do that. It's right. You mix acid, leftover base, and you neutralize it. So now what's our pH at neutral? 7. You neutralize it and you just have a salt and water. Guess what you can pour down the drain? Salt and water. We do that all the time. Okay, so let's do this. Balance the following neutralization reactions. Let me erase this stuff. Okay, now that we got room. All right, so we have HNO3 and MgOH2. HNO3 plus MgOH2. Okay, so what's going to happen? Do you see something that could make water? Do it just like I did before, where I'm gonna say, okay, here's a hydrogen for water. Now, what else does water need? A hydroxide, right? Okay, so let's pull that out and say, okay, I know we're gonna make water. What's left? So the Mg is left. So we're gonna put Mg, and what else? NO3. Now, you have to make sure that the charges are correct. I just made an ionic compound, right? Mg is a metal, and NO3 is a polyatomic ion. So I just made an ionic compound. But is my formula correct? No, it's not. What's the charge on Mg? Mg is 2 plus. What's the charge on NO3? -1. So I have to cross them over, right? So I get Mg1. Okay, I'll leave that. But then my NO3 2. Can I just put a 2? Do I have 32 oxygens? No, I need 2 NO3 molecules. So I'm going to put NO3, I'm going to try at least, to put NO3 in parentheses and put a 2 on the outside. So now the formula is correct. Now I have one other step to do. Is my equation balanced? Is it balanced? Yes or no? You have 1 Mg on both sides. Look at NO3. I have 1 NO3 molecule here. How many NO3 molecules do I have here? 2. I have 2 of them, right? So I'm just kind of counting my polyatomic. So I need to put a 2 here in order to get 2 NO3 molecules here. But now, what happened? I have another H. But think about this. To make water, I have 2 hydroxides and 2 hydrogen ions. So how many molecules of water do I make? 2. Okay, last one. We have HCl plus NaHCO3. What are we going to make? A salt, water, and I see carbon. What am I going to make? Carbon dioxide. So like you can even go ahead and put it. I know I'm going to make water. I know I'm going to make carbon dioxide. And now we just got to figure out what's left. So I took a hydrogen from here to make water. I took a hydrogen from here and I took 1 oxygen. So what am I left with? Right? I took 2 hydrogens and an oxygen. I'm left with a carbon. So this is really a carbon, and I have 2 oxygens left. So I put a carbon and 2 oxygens there. So what's left? NaCl. Am I balanced? And are my formulas correct? Right, it's NaCl. You know that's correct, right? But am I balanced? Yes. Don't forget to put your states of matter. I didn't really have room, but put your states of matter. Water's a liquid. Water's a liquid. Carbon dioxide is a gas. Everything else is going to be what? Aqueous. Okay. Y'all have a very happy Thanksgiving. I will see you again on Tuesday, next Tuesday, so a week from today. Anybody on Zoom need anything? Pretty good? Okay. I'll go ahead and end the Zoom.